All right, in this video, we're going to look at rationalizing fractions that have complex denominators. So let's explore this word complex just a little bit. Okay, we've used real numbers for many years. So you started off when you were a little kid using these kind of numbers, just the whole numbers. And then as time went on, you learned about fractions and decimals and repeating decimals. And then you started talking about square roots and numbers like pi. But all of these numbers have in common that they are real numbers. Last year in Algebra 2 is the first time you ran into imaginary numbers. So imaginary numbers have an I in it, right? So this one's got an I, this one's got an I. This one, well, it doesn't have an I. Why is it there? Well, if we simplified it, that square root of a negative would become an I. So all of these are examples of imaginary numbers. Now, a complex number is just a real number and an imaginary number put together. The real part always goes first, and the imaginary part always comes second. And they're either added or subtracted. And it doesn't matter how simple or how complex those numbers might be. Complex meaning like it's a fraction or a decimal or a different square root or something. But if there is a real part and an imaginary part added or subtracted, then this number is called a complex number because it's real and imaginary put together. So when we do our simplification today, these are the kind of numbers we're going to be looking at in our fractions. Okay, so let's look at this one. This is one like what we did in our last video when we talked about this. And if you recall, when we were ready to rationalize this, remember rationalize is the process that we use to get rid of the radical in the denominator. And when we were ready to rationalize, we multiplied by what we called the conjugate. And remember, the conjugate was those same two numbers that are in the bottom, 1 and square root of 7. It's just that the sign in the middle was different. So instead of having plus like we had in our original, they changed into subtraction. So this, remember, was called the conjugate. And then if we wanted to simplify that, I have 1 times 2. I have a monomial times a binomial. So I'm going to distribute that 3 to both of those. And when I distribute, what I'm going to get is 1 times 3 and 3 times the square root of 7. And then in the denominator, remember we have 2 times 2. We have a binomial times a binomial. And anytime we have that situation, we have to FOIL. So we started off by distributing the 1. That was the F and that was the O. All right, so 1 times 1 is 1. 1 times negative square root of 7, negative square root of 7. And then we went back and we distributed the square root of 7. So that's the I and the L in FOIL. And so the inner square root of 7 times 1 is positive square root of 7. And then last times last, square root of 7 times square root of 7 is square root of 7 squared, which we know to be 7. And that's negative because positive times negative is negative. And then we looked at the fact that when we multiply by the conjugate, we purposefully set it up with opposite signs so that those two in the middle would cancel. And then we simplify. Well, in the numerator, I don't have like terms, nothing to simplify. And then in the denominator, 1 and negative 7, those are like terms. That gives me negative 6. And then I look at all the numbers on the outside to see if anything will simplify. 3, 3, and 6 have a GCF of 3. So I'm going to divide all of those by 3, not the 7, because it's on the inside. We leave it alone. All right, and then remember we talked about how in standardized testing, they'll never leave that negative down here. What they'll do is they'll change that negative to a positive, and they'll distribute the negative up here. And that's the answer that you would see on a standardized test. Okay, so let's take this process that we practiced with real numbers and let's look at what happens when we use imaginary numbers, or in this case, complex numbers, because you can see I have a real part right here and an imaginary part right here. So that is a complex number. What we're going to do is we're going to multiply by the conjugate of this one, but because the number is complex, we call this one the complex conjugate. Not complex because it's any harder than this conjugate over here, but complex because it's a real and an imaginary put together. So look, the 1 is the same, the 7i is the same, but this one is positive and this one is negative. So it's the same rules for making the conjugate as what we had over here. We leave the numbers the same and change the sign in the middle. All right, and then the simplification part is going to be very similar as well. So up in the top there, I'm going to distribute that 3 to both of those. So 3 times 1, 3 times negative 7i, negative 12, oops, that's a terrible looking I there. My finger slipped. 21i. Okay, and then in the denominator, just like we did before, I have 2 terms here and 2 terms here. This is a binomial and this is a binomial. So I'm going to need to FOIL. So I'm going to distribute the 1. That's the F and the O. 1 times 1 is 1. 1 times negative 7i, negative 7i. And then I'm going to do the I and the L. I'm going to distribute that 7i to both of those as well. 7i times 1, positive 7i. And positive 7i times negative 7i. Okay, well, 7 times negative 7, that's negative 49. And I times I is I squared. Okay, in the numerator, anything to simplify in the numerator? Nope, those are not like terms. So I'm just going to write those down. And then in the denominator, do we have any like terms in the denominator? Yep. So we have the negative 7i and the positive 7i that are going to cancel out, just like the positive and negative square root of 7 over here. Again, because we set those up with opposite signs, they're going to cancel out. Now this one, let's look at that for a second. Do you remember that we said by definition, I is the square root of negative 1? I'm going to write that right here. Let's see. I equals the square root of negative 1. And if I square both sides, then I squared equals negative 1. So this I squared right here, I can replace that with a negative 1 because I squared and negative 1 are the same thing. And so what I have in the denominator now is 1, and then over here, negative 49 times negative 1 is positive 49, right? Because negative times negative would be positive. In the numerator, still nothing to simplify, no like terms. And in the denominator, 1 plus 49 is 50. And then you want to analyze 3, 2, and 50. Is there anything that will divide into all 3 of those besides 1? And the answer is no, so we are finished. That is our final simplified answer. Notice we have rationalized because there's no I in the denominator anymore. All right, let's do another one of those. Let's try this one. All right, this time I've got still that monomial on top, and I have a complex number in the denominator, right? There's the real part, negative 3. There's the imaginary part, negative 5i, and they're put together, so that makes it complex. Okay, so let's do the conjugate. So remember for the conjugate, the negative 3 doesn't change, the 5i itself doesn't change, but the sign in the middle is opposite. Okay, and I'm going to write the words over here so you guys can see what I'm saying. Just make sure everybody understands me. This thing that we're multiplying by is called the complex. Oops, that should be an N. Complex conjugate. Can't say one word and spell another. Complex conjugate is what we have right there. And it's a conjugate because the signs are opposite. It's complex because it has a real part and an imaginary part. Okay, so let's multiply those together. In the numerator, what do I need to do with the 2? Right, I need to distribute to both of those. You don't have to have like terms to multiply, only to add and subtract. So 2 times negative 3, negative 6. 2 times 5i is 10i. Okay, now in the denominator, let's FOIL that out. In the denominator, I'm going to multiply negative 3 times both of those. When I distribute the negative 3, that's the F and the O. The first times the first, and also multiplying the outer ones together. Negative 3 times negative 3 is positive 9. Negative 3 times positive 5i, negative 15i. Okay, so now we need to go back and we need to distribute the negative 5i. So that's the I part of FOIL and the L part of FOIL. I for inner, that's the 2 terms on the inside, and L for last, that's the last term in each of the binomials. Okay, so let's multiply those together. Negative 5i times negative 3 is positive 15i. And the last times the last, negative 5i times positive 5i. Well, negative times positive is a negative. 5 times 5 is 25. I times I is I squared. Okay, let's see what we can do to simplify that. In the numerator, can I add the negative 6 and the 10i together? No, I cannot. Those are not like terms. So we're just going to write them both down. Okay, now let's look and see what happens in the denominator. In the denominator, we set it up so that these in the middle would cancel. Our whole goal with rationalizing is to get rid of the square root. And so we're going to be able to get rid of those two in the center that have I. All right, and then think about what we said about I squared. I'll write it back up here again. If I is equal to the square root of negative 1, then what do we know that I squared is equal to? Well, that's the square root of negative 1 squared, and we have said several times that squared and square root are opposites. They cancel one another out. So I squared equals negative 1. So I can come back right here where I have the I squared, and I can replace that with a negative 1 because I squared and negative 1 are the same thing. So I still have that 9 right there. Negative 25 times negative 1, negative times negative is a positive. Positive 25. Okay, in the numerator, still can't simplify anything. Those are not like terms. So negative 6 plus 10i. And then in the denominator, 9 plus 25, add those together, and I get 34. And then I always want to go back and check if I can simplify. 6, 10, and 34. Is there anything that will go into all three of those? Yes, they're all divisible by 2. So 6 divided by 2 is 3, 10 divided by 2 is 5, 34 divided by 2 is 17. And this time that's a positive, so I don't need to worry about switching around my negative in any way. That will end up being the final answer. Negative 3 plus 5i, all divided by 17. And y'all be careful that that division symbol goes all the way across. Make sure that it's from the negative 3 all the way under the positive 5i.